Okay, so this will have nothing to do with what happened this morning. But this will have a lot to do with Miguel's talk and Luca's talk yesterday. So also, of course, thanks to Phil and Patrick for inviting me to come here. So this is going to be based on a paper that we put out recently. The reason why I'm giving this talk, by the way, is also because Miguel was not going to give 2 talks, and Janina Rank and Francesco Montanari could not be here, and they work a lot for this. So credit is due. Okay, so this is basically what I'm going to do. So I'm going to describe, so this is going to be about analyzing the observational viability of the Galileon model. So I'm going to start by telling you what exactly do I mean by the Galileon model, then tell you what we did, in particular how did we place constraints on this model, then our results, and then what there can be done next, if anything. And my conclusion is going to be pretty much that at the cosmological level, it has never been shown in a robust and concrete way that cosmological data rules out this theory of gravity, but there are plenty of problems and other possible ways in which we can achieve that. Okay, so what's the Galileon model? Well, by this time, you're probably sick and tired of looking at these equations. So this is the most general blah, 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 blah. So, this is, what I mean by Galileon model is the Nicholas et al. Model covariantized in the way of the Fayette et al. In which you promote the partial derivatives to covariant ones, and you add where? These couplings to curvature in the quartic term and in the quintic term. So this model has no pre-functions, which is something I like about it. And it has, so your freedom is in the value of these 5 constants. Here it has a GR limit when these 5 constants go to 0, but it doesn't have a lambda CM limit, meaning there's no choice of these parameters that makes this whole thing here behave like R plus a cosmological constant. And also, just for completeness, I will always consider the case in which C1 is equal to 0. This is done just for simplicity. It's basically getting rid of this rather uninteresting term, which is a linear potential, at least in comparison with all the other ones. So just a word on how we treat the background. So this model has the so-called tracker background evolution, so where there's a range of initial conditions for the background field that eventually merge an evolution that is characterized by this thing here, so phi dot times h is equal to a constant. And this traces back to a paper by myself and Bauju and others a couple of years ago, in which we found that if the Galileon model is to have any chance at fitting the CMB temperature power spectrum, then this tracker evolution must be followed sufficiently early. And sufficiently early means at least before the acceleration begins. So for simplicity, what we're going to do is just assume that, and it's important to note that, so basically the probability distribution of the initial value of the Galileon field is basically flat and then cuts off here. So if you are below this region or below this value here, it doesn't matter. The physics of the model or the goodness of fit of the model doesn't change. So for simplicity, we can assume that the tracker is followed at all times, and it simplifies our life numerically because then the background is given by an analytical formula, and we no longer need to solve it numerically. So at the end of the day, the Galileon model is characterized by 5 parameters. 2 of them, and in this case just for illustration, Xi and 3 can be fixed by the conditions to yield a given amount of spatial curvature, which I'm going to assume to be always 0, and the condition to be on the tracker. We can also fix another parameter to break this, what I call this unphysical scaling degeneracy. So basically, these are too many constants. So if you try to constrain this, basically, it's illustrated here. If Xi goes to B times Xi and the CNs are divided by powers of B, where B is a constant, so this doesn't change the equation. So if you try to constrain this, your Monte Carlo Markov trains will never constrain. So basically, the easiest way to break this degeneracy is just to fix one of the parameters. It can be any. We chose it to be C2 and to be equals to -1, just to make the equations look a little bit nicer.
So that's the annotation is the wrong sign, right?
Yes, but the sign of the C2 is also an observational requirement. And at the end of the day, your free parameters are 2. So in the rest of this talk, whenever I say the words cubic, quartic, and quintic, I'll be meaning the following. So the cubic is when these 2 parameters, C4 and C5, are 0. So the cubic model has the same number of free parameters as lambda CDM. The quartic is only when C5 is constrained to be 0, and the quintic is the most general one. The C's can take on any value. Okay, so what did we do with this model? So our constraint methodology can be divided into mainly two parts. The first one, we placed constraints using CMB and BAO data on the model. And then in the second part, after pinning down the regions that stand a chance of being cosmologically viable, in the sense that they fit the best data sets that we have, Then we're going to look at the ISW effect, and more specifically to the cross-correlation of CMB temperature maps with the galaxy distribution of galaxies in the WISE survey. So step number one is pretty straightforward. This is just standard parameter inference. So perhaps just emphasize that we're going to be using the Planck 2015 data for both temperature and lensing. And we are using a slightly outdated BAO compilation. So BAO 13 here means the compilation of BAO data that was used by the Planck 2013 analysis. And the reason why we're doing this is, I'm going to explain this later on in this talk, and these are the cosmological parameters that we vary. So in addition to the Galileon ones, we're varying the 6 standard ones in LMDA, and note, though this is important, that we'll also allow the sum mass of the 3 acting neutrinos to be a free parameter, as we should, because we do not know their value. And our analysis was carried out by coupling the Monty Python package with the high-class code that Miguel already described yesterday. Yes. OK, so this is pretty standard. Not assuming flat, we'll just be adding omega k here, one more parameter. So now I'm going to say a few words on exactly how we perform this step 2 here. So at the end of the day, our goal is to compute this quantity, the WISE ISW signal, which is just the cross-correlation of CMB temperature with galaxies in the WISE survey. So it's given by this integral. There are 3 quantities here. At the end, the metapower spectrum. And these 2 kernels here. The first one is the ISW kernel. So characterized by, so given here in terms of time derivatives of the lensing potential, which is what characterizes the ISW effect. And then the second is this kernel, this galaxy distribution kernel. So here, this W function is just the redshift selection function of the WISE galaxies, how they are distributed along the line of sight. And they also have here this bias parameter of the galaxies, which we do not know. And this bias, so basically, if you trace everything back, the amplitude of the ISW signal is proportional to the bias. And if you do not know the bias, the 2 things would be degenerate. So we need to find a way of fitting for this galaxy bias first. And the way we do this is instead of looking at, now the goal is to fit for the galaxy bias, and instead of looking at the cross-correlation of CMB temperature maps with the galaxies, we're going to be looking at the cross-correlation of CMB lensing maps with the same galaxies. The equations look pretty similar, but now basically instead of having the ISW kernel here, we have the lensing kernel. And so the idea now is using data for this quantity. Remember the cross-correlation of lensing from the CMB with the WISE galaxies. We use this to fit for the bias, and then we come back, plug the bias here, and compute the ISW signal. Just to give you an idea of how the data and the predictions look like. So this is the CMB lensing galaxy cross spectrum. Those are the data points from this paper by Simone Ferraro. You cannot tell the different curves apart from lambda CM and the cubic, quartic, and quintic models. That's the point. But what's important here to emphasize is that these curves here are for different values of the bias of the galaxies as they should. And this demonstrates the importance of fitting for the bias. Had I assumed the same bias for all models, I will be getting slightly different results. Then armed with the values for the bias, then we can go back and compute the ISW. And so basically the ISW plot looks like this. There are a couple of curves here, but this figure, well, I'm just showing it for now, but it will appear many times as I go along. OK, results. So first, a few words on cosmology. Miguel has already emphasized a few of the points, but I want to do it again. So what I'm showing here is the CMB on the left, the CMB temperature power spectrum. On the right, the CMB lensing power spectrum. There's the data. There are the curves. And the reason why you cannot tell the different curves apart very easily is precisely the main message of this point, which is that for these 2 data sets, lambda CDM and Galileon model display essentially the same goodness of fit. Yes, this is for the cubic Galileon, cubic, quartic, and quintic. And so the cubic is this red curve here. It's a slightly higher ISW, but here we are in the large error bar region, so we cannot say much here. What is interesting, in my opinion, is that the same goodness of fit is achieved with very different constraints on parameter values, and Miguel has already showed this figure. 2 noteworthy examples are the cases of H0 and sigma mu. Miguel has already pointed that out, but I think I never lose a chance of whenever I show this figure to point out that there's no such thing, as I hear many times people saying, as the H0 value from Planck or as the constraints that Planck gave on sigma mu. Planck just gives you maps of the CMB, of temperature, lensing, polarization, whatever. These parameters only come after you throw a model at the CMB. And if you use different models, you're going to get different constraints on these parameters. And as Miguel mentioned, no one here is claiming that this solves the H0 problem, but it's also super helpful to keep in mind that there are theoretical ways out of current tensions in lambda CDM. Okay, so this is basically, in this part of our analysis, is basically a confirmation of the results from a paper by myself and Baju from 3 years ago. So this is where the new parts begin. So we focus now on the ISW. So this slide here is going to be a little bit busy at the end of it, so I'm going to go slowly. So this is for the quartic Galileon. The next slide for the quintic is going to be pretty much, it's going to have pretty much the same structure. So this is constraints on C3 and the Xi parameter. These are 1 and 2 sigma contours from the CMB and BAO constraints. And the points here are, so these are the points accepted in the MCMCs, and they are colored according to basically the colors mean the ISW, the chi-square fit to this data here, but there are 2 color bars here, a reddish and a greenish one, and the meaning of this is the following. So we define this ISW amplitude, which is just, this is just to facilitate reading these figures, which is just the theoretical values, so the sum of the theoretical prediction evaluated at the L bins of the data normalized by the sum of the data. So red is a negative amplitude for this figure here, which is bad, because the data predominantly lies in the positive part of this figure, and green means good. And as you can see here, there are green bits in the corner of these 1 sigma contours, and that's kind of like the main takeaway message from this slide, which is in the quartic and in the quintic, as you'll see in the next slide, there are CMB and BAO compatible parts of the parameter space that also yield good fits to the ISW. Just here as an historical remark, in this paper from 3 years ago by myself and Baju, we were perhaps too quick to say that the ISW was the likely killer of the whole Galileon parameter space, including the quartic. And the reason why we said that, because this point here was basically the same best fitting point that we found at the time, and we analyzed the predictions for this point and some points around it. And we concluded that, okay, odds are that the ISW is going to rule out this because this lies in the negative part of the so the colors here are red, so negative amplitude for the ISW. So basically what we missed, we failed to appreciate the fact that there are maybe corners at the end of the 1 sigma contours that can have a positive sign for the ISW. So as I said, so the picture between quartic and quintic just changes at the quantitative level. Qualitatively, the same conclusions remain. So the quartic and the quintic pass the ISW test, at least for the WISE sample. The cubic doesn't. So when Miguel and Lucas were saying that the ISW was ruled out at the 8 sigma level, they were borrowing a result from this slide. So this red curve here is the best fitting cubic Galileon model to the ISW data. So this is the best that you can do, and this is basically amounts to an 8 sigma tension. So I added this side comment because this was part of discussions yesterday. So what this means here, so the cubic Galileon, now making a comparison between the Galileon model and the cubic Galileon model and the more general G3 term in Horndeski. So what this means that we're ruling out perhaps the simplest G3 form, which is the one that is linear to X, and there's this paper by Kimura et al. Where they show that if you just add a simple modification, which you add a power of n to this functional form, you can discuss whether or not this yields a beautiful model or not. But if n becomes large enough, and large here I mean of order 1,000, it's possible to evade these tensions here. This is just to provide a bit of physical intuition for the results here. So what I'm showing on the left is a time evolution of the lensing potential, and on the right the corresponding WISE ISW signal. So in black is lambda CDM. So to build intuition, what happens in lambda CDM is in the matter era, so in the far right of this panel here, not shown, the potential is constant, and when the acceleration begins, the acceleration causes the lensing potential to decay. In the cubic Galileon, and this yields corresponding a positive amplitude for the ISW signal. For the cubic Galileon model, which is red, so you have the same thing. So in the cubic Galileon model, the acceleration is also working to decay the potential, but here there's a much stronger effect by the 5th force, which makes the potentials deeper. Then in cyan and magenta, we have the curves for the Galileons, and basically the main point here is that so they have, now there's more freedom because now you have more parameters, and there are these non-trivial evolutions of the lensing potential. And exactly what's happening here is that this band here, which is the redshift distribution of the WISE signal, is picking up the time evolutions of the quartic and quintic model that happen to be decaying during the redshift range that is spanned by the WISE galaxies. And basically, the cubic Galilean model does not have the flexibility to have non-trivial evolutions of the evolution of its lensing potential. Okay, so not everything is a walk in the park in cosmology. So this is now basically explaining what we mean by, or what we use this slightly outdated BAO 13 data set. So because we were aware of, or we became afterwards aware of these tensions or potential tensions with more recent BAO data points. So to guard against running Monte Carlo chains with inconsistent data sets, we prefer to use a BAO compilation that we knew was consistent with the CMB. So we were after only the constraining power, and then analyze a posteriori the resulting goodness of fit for these more recent BAOs. This plot is a bit hard to follow. So there are basically here 3 distant measurements. Solid is lambda CDM, dot and dash is quartic and quintic. The field points, the open simple, this one, and this one are the ones we use in our MCMCs, and the field ones are the ones we didn't use. But basically, just here I'm just guiding the eye. There are basically 1.5 and 2.5 sigma tensions with this BAO data set. So even at the level of cosmology, for the quartic and the quintic, despite passing the ISW test, there are chances that more precise, or even these ones already, depending on your opinion, more precise BAO measurements will be able to rule out these models in cosmology as well. Okay, how long do I got? Plenty of time. Okay, so what can be done next? So the next few slides are going to be just like very quickly going through many possible ways in which we can test and potentially rule out the parts of the model that survive the cosmological scrutiny. So this is again showing so this is what I call ISW tomography. This is showing the time evolution again of the lensing potential. And so these solid curves here are the ones that have a good fit to the Wise ISW signal. And so because like lambda CDM, they are decaying during this redshift range. But you see that there are other redshift ranges where this evolution is growing. So if I have another galaxy sample, and if I now try to cross-correlate with a galaxy sample that lives in this redshift range, then I have another chance of telling these models apart from lambda CDM. So this sounds, explain sounds easy, but these measurements here are measurements on very large scales. Cosmic variance plays a critical role here. It's interesting to conceive the idea of having ISW tomography constraining non-trivial evolutions of the lensing potential. Whether or not that will yield tight enough constraints, that's a separate question. Another thing you might be wondering is why didn't we use other cosmological data sets that you might be thinking of? An obvious one that may come to mind is the growth rate. So typically quoted in terms of this quantity, F sigma 8 is a function of redshift. And the reason why we didn't do that is because we did the right thing. So a lot of people, too many people fail to realize or fail to appreciate that these points here are not direct measurements. These points here are obtained or are derived by processing galaxy clustering data with very elaborate models of redshift space distortions, galaxy bias, and prescriptions for nonlinear structure formation. And these models were developed having lambda CDM or GR in mind, and they are only validated in galaxy mocks of lambda CDM and GR. So there's nothing wrong with using F sigma 8 measurements, in particular these points here, to test consistency at GR. But if the second you start using these points to constrain modify gravity without proper validation, then that's the second you start to become prone to drawing biased conclusions. And these 2 papers here explain this with a bit more detail. Another potentially interesting question is where do the Galilean contours lie in this sigma 8 omega matter tension? Does it alleviate the existing tension, if there's any tension or not? The reason why this wasn't done at the moment is because, at least for the case of the kids analysis, they go to scales where nonlinearities become important. So you need to have a prescription for nonlinear structure formation, including screening, that's currently unavailable for the Galilean model. So basically here, this has to be deferred for future work until these prescriptions for nonlinear structure formation develop, or instead we only use very large scales, but this will also diminish the constraining power of this cosmic shear data. Okay, so this is my last slide before I summarize, and I'm going to mention 3 what I call here 3 guns that are pointed at the quartic and the quintic. This one here is one that wasn't mentioned neither by Miguel or Lucas yesterday. So so experiments that could be done with linear laser ranging. So let me give you an example. So for the case of the quartic Galileon model, the Poisson equation can be written schematically in this way. So basically 4 pi, some term, g delta rho, and then a fifth force term. So this function here depends only on the background value of the Galileon field. This one depends on spatial gradients, these two here. So because they depend on spatial gradients, once you go to the nonlinear regime of structure formation, these are the terms that screening will cancel. But this is a background term. This is just a function of time, so the screening will not do anything about this term. And what this term will do is basically if you multiply this by that g here, this will look like a time-evolving gravitational strength. Now, under the assumption that the phi bar dot that is inside this function is the same, so the one that we would feel here locally is the same in cosmology, then you can do the math, and this quantity here will be larger than this bound that comes from lunar laser, ranging immediately ruling out the quartic and almost like the quintic as well. So this is a very serious game pointed at the model. One caveat I can think of, and I'm super happy to hear discussions about this, is this true though? Like, can we just take the cosmological value of the scalar field and just plug it when we make a prediction for the solar system? And I've talked to many people, and this is currently, to me at least, an unanswered question. Don't ask me. It's too large for it to be compatible with that.
An order of magnitude larger?
Yeah, we're talking about an order of magnitude larger.
2 times h naught is the value of time is the derivative of the
Then there will be 2 orders of magnitude. Then this has been mentioned already in the conference and over drinks. You know, light versus the propagation of light and gravitational waves. So if CT is smaller than C, then you can rule out, Miguel showed that you can rule out the quartic by the Cherenkov radiation argument. And now with LIGO online, potentially tighter constraints will become available in case LIGO detects a gravitational wave with a known optical origin. And these are, again, 2 more very serious guns pointed at both these models, the quartic and the quintic. Okay, and this is something I asked Lucas yesterday, and okay, this might be a long shot, but this all relies on assuming that screening is not playing any role in these calculations. This might be a long shot, but anyway, to be on the safe side, I wonder, and I urge people to keep wondering whether or not screening or anything else can offer a way around of these 2 tests. So this is the last point I want to make. This, again, has never been mentioned in this conference, at least that I've heard. So when you work in the quartic and quintic, this is also true for the cubic, by the way. When you start going into the nonlinear regime, weird things start to happen. And by weird, I mean the solutions for the fifth force, solutions for the spatial gradients of the scalar field start to become complex numbers. So this is just an example for the case of the quartic. What is shown here is so this effective gravitational strength as a function of the density contrast in voids. It's negative, and time in the y-axis. And you see that at late times and for sufficiently low values of this density, the physical solution simply ceases to exist. It becomes a complex number. And again, I'm happy to discuss what's the meaning of this. And this scans the cubic, quartic, and quintic. Are we solving the wrong equations? Have we made an approximation that we should not have made, et cetera, et cetera? Again, this is a result that goes back 4 years ago, and to this date, I still haven't found a convincing answer or for what is the meaning of this. Okay, so to summarize, well, the cubic Galilean model, or in other words, the simplest G3 part of Horndeski is ruled out at the 8 sigma level by the WISE ISW signal. The quartic and quintic, those survive despite some existing tensions with BAO, but the quartic and quintic have many guns pointed at them in cosmology. Valjo also mentioned void lensing as well, because these models are also likely to be very tightly constrained by such measurements, and on the astrophysics side, there's also many ways. So I don't think we are at the stage where we can definitely kill these things, but maybe after October, maybe not, we'll be able to. Okay, that's it. Thanks.
So to come back to this lunar ranging thing, I mean, the way I would think about it is that okay, this is assuming FRW, of course, but on these attractors, the value of phi dot is a function of the density, essentially. So if you think of the inside of the galaxy as being essentially a time-shifted cosmology, you know, sort of density is equivalent to the density in cosmology would have been at redshift of, I don't know what, 110, I'm not sure. Then that value there locally in the galaxy would be something like the value of phi dot at that redshift when the densities were equivalent, I would say. That would be my guess.
To get an order of magnitude estimate for...
Yeah. Now, of course, really the galaxy is actually symmetric and not FRW.
Yeah, that you are assuming FRW again, and it's, you know, when people, the first thing people do when they start making predictions for the solar system is to perturb around Minkowski. So the second I start doing that with this model, then this term here will not be there simply because there's no scale factor in the Minkowski metrics. This arises because we multiply the spatial sector of the metric with the time-dependent function.
Yeah, but it's not Minkowski either, because I think it's sort of there was this phi dot in the universe, the galaxy collapsed. There'll be some remnant of that left. You're not really...
But that's a very hard that's a very hard calculation to make.
But I think this may be also related a little bit to this imaginary stuff that you're finding. This kind of...
Yeah, I mean, all of this, of course, very approximate, not consistent. Right? I mean, you really have to solve the full, if you want to see what happens with the time dependence, you have to solve the full time dependent equations. You can't say, I take the quasi-static limit for the perturbation, but keep the time derivative for the background part. Right? So you have to solve the full.
Yeah, but that was addressed by Hans Winter and Pedro Ferreira. They have a paper in which for spherical symmetric configurations, they go beyond the quasi-static approximation and they find the same problem. They couldn't, so this cannot be eased by relaxing the quasi-static approximation. That's the conclusion of this paper by Winter and Ferreira.
Sorry. So then if they found that if they found that, yeah, then I'm confused. You're saying we don't know what phi bar dot does, but then you say Hans and Pedro know what phi bar dot does. So which one?
No. Okay, so let me try to explain. So this equation here is valid for cosmology, and this equation here is derived under the quasi-static approximation. So question number one, so relaxing quasi-static approximation, so having here time derivatives of the perturbation of the field, is that going to ease this problem? And this is what they addressed. What I'm questioning is whether what do you plug in for the time evolution of the scalar field locally?
What they found, right? Which is?
No, but they also work in FRW. They're still working at the cosmology level.
In that paper,
Yeah, well, hang on, I'm confusing. Yeah, it's not here. No, they are addressing this issue. Sorry, they're addressing this issue. Sorry, I was completely confused. In Winter and Ferreira, they are addressing the issue of the complex. So they found that relaxing quasi-static approximation does not ease this problem here. They don't address this one.
Yeah, but as a first approximation,
yeah.
We take an overdense, spherically symmetric overdense object inside FRW, and look at, ideally, it's also collapsing.
Okay, I see what you mean.
Look at phi dot, what total phi dot
does. Yeah. I agree, yeah. That's a way of taking a step in the direction of answering this question.
Regarding that phi dot problem, what is the question about phi dot in the solar system? Just like to point out that we have a paper showing that if you have scalar waves coming into the halo and the speed of sound is funny inside the halo, then phi dot will not be the same outside the halo and inside the halo, just because the waves are perturbing your phi dot. I don't know if you look at that paper.
I'm not particularly interested in solving this problem. I want someone to do it and then tell me the answer.
Okay, welcome back. No. So thanks again, Alex.